This is a webinar on humidity, how to manage humidity, primarily within homes. That's our focus. I'm part of Build Equinox, a small company in central Illinois, and we're the developers and the manufacturers of something we call the SERV Smart Ventilation Unit. And you can read about that, which is not our primary focus of today's talk, on our website. And any of you that are not familiar with us, there's a lot of newsletter articles as well as reports similar to our topic today on humidity. We're very research oriented, very data driven, and we want to share that information with you to help you design better homes, more efficient homes, more sustainable homes, and especially healthier homes. Our mission as a company, and many of you may already be familiar with us, but it's in the simple words of Aldo Leopold: how do we live on a piece of land without spoiling it? Living on our daily allowance of solar energy. And so I'm speaking to you from a 4,500 square foot Morton building where our business is located. And even though this is a steel sided simple building, it's a net zero building. It's solar powered with 8.5 kilowatts of solar PV, features a geothermal heat pump for heating and cooling, as well as Minisplit air source heat pump, and then other systems that we are involved in researching and developing. Our primary goal within a house and our primary focus with our smart ventilation system is helping us be healthier, helping us be more productive, making our brains function better, and sleeping better. And all of these, of course, are interrelated. So that's where we're coming from, but we can't just ignore how the rest of a house operates. We're part of this overall system, and humidity, which often gets neglected, or people just wish and hope that maybe things will get handled okay. There's no need for that. There's no magic to it. It's a basic engineering area that we've dealt with for a long time. And so that's what we want to address today, is this aspect of humidity. As far as humidity in buildings, we've been addressing this for well over 100 years as far as today's active air conditioning systems. For sure, we've been dealing with it for much, much longer than that. The first air-conditioned building in North America is this grand old building in Brooklyn, New York, and in 1906, a young engineer named Willis Carrier designed the first building cooling system that was installed here. But it was for dehumidification, not for cooling. And the reason why dehumidification was of primary interest was that this was a printing company, a lithography company, and during New York's humid summers that they had to shut down the printing presses. The ink wasn't drying properly. Upon the success of this building, Willis Carrier went on to bigger and better things as he formed his own company. The second air-conditioned building, as I understand, was a stock market building on Wall Street. As our productivity, our ability to think, our ability to get things done is related to our comfort. And Wall Street was quick to see that maybe they could gain an edge on things by being more comfortable in their buildings. This is what happens when you don't manage humidity. This is a little coffee shop in Amherst, Massachusetts I was passing through. You were getting dripped on the inside, the windows were dripping, and beyond just the discomfort and getting drops on your head here and there within the shop is health. When you have this situation occur, and when it occurs frequently, you're going to have mold and you're going to have other air quality issues that impact your health. And we don't have to just rely on hearsay or hand waving. There's real data that shows too moist of an environment in which molds grow, are not healthy environments. This data comes from a recent report, which is located on our website, that we analyzed data from another report that was written earlier in 2019 on military family housing, privatized military family housing, and basically the state of military housing for our families is horrible. And this plot is from around 100 different military facilities representing about 10,000 people. So this is a lot of data. And from the Military Family Association Network, which conducted this survey, basically they found that 1 out of 4 homes with mold has someone in that home with an environmental illness, and that many of these homes, so each dot represents a facility somewhere in the range of 50 to maybe 200 housing units with anywhere from 1 to maybe 5 to 6 occupants in the home, that these are failing. And the health, the readiness, the productivity of the people living in these homes was also poor because of the building. 40% homes with mold, which is unacceptable, results in at least 10% of the occupants being sick. And it's not necessarily that the mold is causing the sickness, but mold is also a surrogate for poor air quality in general. And again, you can read more detail on this report and other data in this report related to these issues. Our outline today, we have a 4-part series, and we've released 3 of those reports, and the 4th will be released in November on humidity and the different aspects of humidity from part 1, which details how we determine how much moisture management we need for a home. Part 2, which then looks at climatic characteristics of humidity, and a lot of it's common sense. The southeast of the United States for sure is very humid and requires very high levels of moisture management, whereas the southwest, not so much. The Intermountain region, Colorado, Utah, again, not so much moisture management, but you get to the Midwest where we live, the Northeast and Northern tier, and you hit still some times of the year when you need to dehumidify, and perhaps other times of the year when you need to humidify. The 3rd report that we just released in October covers the ways that we can manage moisture. The common machines that are available now, from air conditioners and heat pumps to our Serve smart ventilation unit, which incorporates a heat pump that also contributes to beneficial management of moisture, and today's advanced technology for water heating, what we call a heat pump water heater or a hybrid water heater, that this also contributes to moisture management. And then finally, when you have too much moisture to be managed by these 3 types of systems, that you need to progress perhaps to a dehumidification system. And then finally, on the humidification side, although we hope with today's homes being built in very efficient and very well sealed manners that the need for wintertime humidity is being decreased. And the benefits of not having to humidify or dehumidify outside of a typical range, then there's big energy savings. And so the fourth part of this and the fourth report that comes out in November considers the whole house. As we look at how much water we need to condense or vaporize, what is that energy impact relative to the whole house? And that will be our final subject today. The bottom line, with all the complexity and issues revolving around moisture management, comes down to a very simple result, whether you're in Florida or you're in Vermont or California. Build tight and ventilate smart. And we'll talk about those as we go through this. Very briefly, for those of you who are interested in various certifications like LEED for guiding how you build a green home, there's points available for managing moisture, from balanced ventilation to enhanced exhaust, bathroom exhaust for humidity control, and various ways you can get points. And hopefully this webinar and our report series gives you a firmer basis for calculating what you need to do to manage your moisture. As far as indoor moisture, these photos are from my house, what we call Equinox house, and you can read several reports and newsletter articles on this house. It's getting ready for its 10-year anniversary, but this is a 0+ house built in Urbana, a very challenging climate in North America with Louisiana hot, humid summers and Arctic blast from Minneapolis in the winters. Just not as much hot, humid as Louisiana and not as much Arctic cold as Minnesota, but we for sure have to be nimble enough to move around in all of that psychrometric space. And as you look around those moisture regions of the house, from the kitchen to the laundry to the bathrooms and where you have plants or aquariums, figuring out how to manage that moisture. And just like to state, these pictures are recent pictures, 10 years of showering most every day in this bathroom, no mold, no deterioration of any of the finishes within this bathroom. The same for the kitchen, which features a recirculating kitchen exhaust for getting particulates and other pollutants away from the cook, but then being managed by our Serve smart ventilation system. And then in the laundry room, a heat pump clothes dryer, which we won't discuss directly, but that does have also beneficial energy performance as well as some impact on moisture within the home. But overall, you can seal a house up as tight as you can seal it. This house is below passive house level of ceiling. It was 0.5 ACH when it was constructed on a blower door test, and that you can manage humidity then with proper indoor air quality, a healthy indoor air quality. As far as occupant moisture, what we generate and put into a house, and you can read the detail and background of this data from our report. Some of this is from data we've collected in the field. For example, our very extensive report on the Vermont homes, a 2-year study of hourly data of all energy uses and air quality and comfort conditions, temperature and humidity in 13 homes located in Vermont. So for example, our cooking energy, which is then related to the amount of moisture put into a house, is based on that data. Occupant moisture basically from our respiration. But of course, if you're exercising, perhaps there's more because you do breathe more, your metabolisms increase, and you perhaps are perspiring, which can be an additional significant load. But all of these add up to somewhere in the range of maybe a kilogram, a liter to 1.5 liters per person per day. There's some scaling as you go to 2 people to 4 people as far as the amount of moisture that might get deposited on shower surfaces and things, as you see here. But somewhere in the range of, say, 1 to 4 liters per day for a typical house occupancy of 1, 2, 3, or 4 people. The other impact as far as moisture, so humans and our activities, we're humidifiers, and everything we do adds humidity. There's nothing I can think of in which is subtracting moisture as far as a human's activity. So we're always adding some moisture. Good in the winter, detriment in the summer typically. Depending on how leaky a house is, this left-hand scale shows you relative to wind speed, how much infiltration air is blowing through a house that would test at a blower door level of 6 air changes per hour at 50 pascals. 6 air changes per hour is a conventionally built home in which, say, additional effort towards sealing beyond conventional construction means isn't attempted. We're dropping down to about 3 ACH, as many building codes are now requiring throughout North America. That would essentially cut this infiltration flow in half. A home with 3 ACH, a 2,000 square foot home, instead of having, say, 400 CFM of infiltration air when it's 20, 25 mile per hour wind, would have about 200. If you drop down to passive house levels of 0.6 air changes per hour, 50 pascals, that would be 1/10 of the infiltration air. And if we look at what's a typical wind speed for most of North America, say 6, 7 miles per hour, we would be looking at about 120 cubic feet per minute of air blowing through your house with that wind speed at 6 ACH, and then maybe about 12 CFM with a much tighter sealed home. But it blows with the wind. When the wind's not blowing, even in a leaky home, you're not getting flow through the house. And this is why a leaky house, and in our smart ventilation report that's posted on our website, you can see more data and more information related to it. But even the leakiest of leaky homes, when there's no wind blowing, will be polluted inside when the wind's not blowing, and it will be overventilated when the wind is blowing. Current ventilation standards. This is a table taken from ASHRAE 62.2, the residential ventilation schedule from the ASHRAE Society, and their 2016 version. It's updated every 3 years, typically. And the problem with ASHRAE ventilation, ventilation's essential, and it's good that there's at least this ventilation schedule, but it does not reflect a healthy home or how to maintain a home in a healthy condition. It does not specify the importance of distribution of that air within the home. So there's a lot more beyond this that's needed. And for example, a 1,000 square foot home with 2 bedrooms, if you put 4 people in it, while the ventilation rate is 52 CFM, if you seal this home up to passive house levels, this house has bad air on average, absolutely no doubts about it. So the air quality is just insufficient. Whereas today's average new home construction is about a 2,700 square foot home in North America, and this ventilation schedule requires 120 CFM. The average occupancy of a US home is 2.5 people, and you find that this house is overventilated, and the schedule requires you to run that continuously. We're going to look at these details. We're just going to pick a 2,000 square foot home, which is similar to Equinox house. It's a 2,100 square foot home. And that way we can also compare some moisture data from Equinox house with the example that we'll consider. Before we work on this example, and without getting into too many details of a psychrometric chart, and just historically, since we were talking about the first air-conditioned building, the psychrometric chart was the brainchild of Willis Carrier as well. He was a very phenomenal, very important person in the HVAC&R industries. He came up with this way to, in effect, linearize moisture changes and temperature changes, what we call latent changes and sensible changes. So sensible goes with the temperature change, latent goes with the hidden humidity change, and both significantly impact energy performance of a building. If we were to look at where most people feel comfortable, somewhere in maybe the 68 degree Fahrenheit to about 74, 76 degree Fahrenheit. Depends on your activity, your personal preference, your clothing, the surface temperatures of walls around you, whether you feel comfortable or not. But most of us in that 68 to 74, 75 degree temperature region will feel comfortable if the relative humidity, these curved lines, is less than about 60, 65%. The left-hand scale on this, which may be less familiar to you, and the key thing to understand is the left side is telling us how much water per mass of air is contained, essentially the water concentration in air, where the weather person on our TV stations is telling us relative humidity, which as relative humidity, it may be easier for them to measure and what traditionally they talk about. But when we're talking about moving moisture in and out, this more absolute level humidity ratio or specific humidity on the left-hand scale is more useful. Somewhere above about 0.011, which basically means about 1% of the air is water vapor, we start getting to where the evaporative cooling effect on our skin is no longer comforting, and we start feeling less and less comfortable. Below this level, we have quite a wide range of tolerance to much lower humidity levels, and usually the low level, which again is very personally decided, will be because your skin is itchy, you're having respiratory sensitivities, you're getting nosebleeds, you're dry skin, things of this nature. And so the lower limit is for someone to decide, but typically around 30% or less is getting to where most people would consider it too low. And then we also have impacts such as flu and cold viruses, which tend to seem to have more longevity in low humidity environments. So another reason why you may want to be 30%, 40% or more in the winter. When we look at the reality of what weather data looks like, and this is an hourly plot of weather data for Urbana. So roughly 8,000 data points shown here and somewhat colored from winter to spring to summer to fall, and a couple of in-between periods of going from spring into summer, or winter into spring called unlocking, and fall into winter called locking. But when we look at average humidity for, say, Urbana, the outside humidity ratio would be about 1.3% water vapor. Humidity ratio about 0.013. And if we consider that we'd like to keep the house at, say, no more than 60% humidity or about 0.01 humidity ratio inside, that difference in humidity ratio is what's driving moisture in and out of the house with infiltrated air. But when we also look at how much humidity we might reach in our location, and actually Miami, Florida, New Orleans, Houston, their peaks are not much different than our peak, as I mentioned. It's just that they have more hours located in that upper range, that they might reach a humidity ratio of about 0.023. So when you look at the difference between 0.013 and 0.01 versus 0.023 to 0.01, you can see that the humidity handling, the moisture handling capacity of a machine can vary greatly from one day to the next. So let's go to an example. And this example and the computations, they're quite simple. And the point about the computations isn't the computations themselves, but the result of it. And for sure, this is where you'd want a computer program such as our Zeros program. Zeros is a simulation program we call Zero Energy Residential Optimization Software. It's free to use software, it's online software, and it's very powerful software for designing net zero homes. It also does financial and economic analysis. And if you're interested in that, you can just send us a note and we'll give you a link to that. We have people around the country regularly using it, from high school and college students in sustainability classes to practicing architects and engineers. So this example, though, we just want to make real that this humidity, that it's not magic, that we can determine what we need to do and then figure out what we have for doing that. So let's say we have this 2,000 square foot home, 3 bedrooms, 2 occupants. ASHRAE ventilation standard would be 90 cubic feet per minute. And if we assume 2 occupants in the house, 16 hours per day, and if we would like to maintain an indoor air quality in which carbon dioxide on average is no greater than 1,000 parts per million, and this is nominally what the ASHRAE 62.2 and the commercial building 62.1 standards are geared toward, then we would have about 20 cubic feet per minute per occupant. And if that occupant, in order to maintain 1,000 parts per minute, per million, and if that occupant is in the house 16 hours a day out of 24, we would need about 27 cubic feet per minute average ventilation rate, which also includes infiltration, door openings, window openings, and other things that are contributing to air blowing through one's house. So if you have kids and they're regularly opening and closing outside doors, or a pet, or you're not opening them, that there's a balance between either the ventilation system or the infiltration system that add up to what you need to manage the indoor air quality. And this is what a smart ventilation system does as far as maintaining the exposure, your pollutant exposure. Now we consider 3 contractors. Contractor Loose is going to build conventional house with 6 ACH, and they're in a location where they're also required to have ASHRAE 62.2 or 90 CFM ventilation. So this house with average wind speeds and that level of ventilation would have about 230 CFM of air flowing through it. Now it changes with the wind blowing, and you can read more about the impacts of wind in our smart ventilation report. But if Contractor Loose decides they want to build a better quality home, they learn how to seal and tighten up a home, then Contractor Tight is building a passive house sealed home at 0.6 ACH, coupled with, again, ASHRAE 62.2 ventilation for a total of 104 CFM. Now, Contractor Smart, with this type of occupancy, smart ventilated home is an automatically ventilated home that monitors air quality, VOCs and CO2, and then brings in fresh air as you need it. When it's windy out, when the doors are open and closed a lot, smart ventilation system senses that and doesn't need to bring in as much air. And when it's not so windy, or there's a lot of occupants, or not so much of a need, it can increase or decrease. But on average for this home, we assume that it needs about 27 CFM to keep air quality controlled. Now, I also want to mention what's somewhat ironic and maybe not so common sense is that a leaky and overventilated home also, we find from our field studies, typically has very poor air quality. And that's because where it leaks or where it's overventilated isn't necessarily occupied. So a home that's just simply dumping 90 CFM of air into the house spreading it into every room of the house, but 80% of the house isn't occupied. 80% of that fresh air didn't do anyone any good. You need other systems, distribution systems, to actively figure out how to move that to where it's going to be beneficial. Now, this 27 CFM may just seem like that's way too small. How could you possibly use that? And again, on our website, you can see live data from Equinox House, as well as archive data from Equinox House for more than 4 years since we added online monitoring capability to serve units. And so feel free to poke through there and look at all of our air quality data, look at all of our temperature and humidity data, and just see that this is real. And I'll also mention, though, that what's the lower limit? Well, we humans breathe around 8 liters per minute at sedentary or typical sitting, moving around office work type activity level. And that equates to about 0.27 CFM. So if we put you in a moon suit and just fed you fresh breathing air, and then your exhaust air would go out directly and not impact the surrounding air around you, we could reduce that 27 CFM by a factor of 100. So here's how we calculate the water balance. This is a simplified equation, but it's a very accurate equation. Multiply 50 times the infiltration ventilation flow rate. Multiply that times the water concentration or humidity ratio difference between the desired inside humidity ratio and the outside. In our case, 0.013 for the average Urbana outside humidity ratio and 0.01 for our inside. And then add the generation of moisture from humans breathing, cooking, washing, showering, and that activity. About 2.5 kilograms or 2.5 liters for our assumed occupancy. We look at Contractor Loose's home in Urbana, and we see that with the 140 CFM of infiltration and 90 CFM perhaps coming through an HRV or an ERV, that we would have about 34, 35 liters of water moving into the house, kilograms of water, and then about the 2.5 kilograms that the indoor occupants generate. So this house, this Loose house, is dominated by outside climatic conditions. We go to contractor type, the same ventilation level, 90 CFM, but now only 14 CFM under typical wind conditions. And now we're getting the moisture loading in the summer down to about 18 kilograms per day, and a significant reduction. And we'll take a look at what that means energy-wise as we move through the example. But going on to Contractor Smart, somebody that also builds a tight house, but now with a smart ventilator, only brings air in when it's needed and doesn't bring air in when it's not needed. And in this case, we see that with a tight house, minimizing the amount of infiltration, and then with a smart ventilator bringing in air when you need it at the rate you need it to keep it controlled. So this 13 CFM is a little deceptive because that's a 24-hour average. But if you had 10 people in there for just an hour or two, the ventilation rate might go up to 200 or 300 CFM for that period of time. And then people leave, and then it ramps back down. And so while you're seeing what looks like a very low level of ventilation, it in actuality is not. Indoor air quality is a very dynamic process. It's also a very complex process spread throughout a home, and one needs to assume more. It's more complex than just simply blowing air into a home to ensure good air quality, good healthy home for the occupants. We knock this down by another factor of a third from contractor tight with ASHRAE ventilation. So much less moisture management, much more resilient as far as moisture impact. So let's take a look at some different climates with the same type of example. We'll look at the peak summer and then the winter, if you can call Miami as having a winter, and look at the characteristics as far as the moisture management. What we'll find is Miami has dehumidification all year, and as dry as we think of Phoenix, it does have a mini monsoon season, as parts of the Southwest do, that requires some dehumidification. And then basically no humidification should be needed in Phoenix for the winter time. And then Urbana, which dehumidification for sure is needed in the summer, and then possibly needed, depending on the construction of the house, humidification in the winter. So looking at Contractor Loose, with Miami having an average summer humidity of 0.018 and a winter of 0.011, we see that while winter does require some dehumidification, because that's so close to what we would like to maintain, the 0.01 inside the home humidity ratio, we don't have much dehumidification in the winter, but in the summer we've got a huge amount, almost 3 times what we have in Urbana, because of the extent and duration and overall high humidity level. Phoenix is lower in humidity during its humid season than Urbana. So instead of 36, 37 kilograms of water or liters of water per day that need to be pulled out in the summer, maybe as much as 25 under the same type of loadings as the Urbana house. When we look at the winter in Miami, as we mentioned, much lower but still needing dehumidification. The winter in Phoenix with 0.005 or 0.5% water in the outside air, when that blows through, that's helping to dehumidify or pull down the moisture generation of the indoor occupant activities. And so by not humidifying, using that same relation that we showed before, you can instead turn that around and figure out the humidity. The relative humidity in this case would be about 32% in this home, this leaky home, during the winter. And in Urbana, you would add about 20 liters of water into the air in order to try to keep it at about 30% humidity. We go to Contractor Smart, or Contractor Tight. We see again, as we saw before, we reduce Miami from about 90 to 100 to about 40 to 50 liters of water per day in the summer. In Phoenix, we've reduced the load almost in half, and then the same in Urbana. As well as in the winter in Urbana, now we're adding maybe about 8 liters of water per day to the homes indoor to keep it at 30% humidity. And then finally, Contractor Smart, bringing in air as needed to manage air quality. Now we're getting down to about 13 liters per day during the average day in Miami summer, much, much less than 90 to 100. A huge impact on the home's energy, as we'll see, as well as making it much easier for equipment to manage this moisture load. Phoenix drops the indoor humidity in winter, comes up to about 40%. In Urbana, we see that we drop down to about 6 to 7 liters of dehumidification during the summer on average. And in the winter, essentially, we don't need to add any moisture to keep at 30%. And as I mentioned, if you look at Equinox house data live as well as archive data on our website, you'll see that Equinox house typically in the depths of winter, January, February, we're at 40% humidity without any humidification. What we do have that's somewhat different is that we have about 50 plants scattered around our house, and we water them at about 6 to 7 liters per week, a little more in the winter, a little less in the summer, but that extra liter per day is what propels us up to about a 40% humidity level during the winter. Now, how do we manage this moisture? There's 4 different systems that we'll discuss for dehumidification, and then we'll talk a little about humidification. And there's much, much more detail about the performance, the energy, required for running these machines in our Part 3 report of handling humidity. And so anyone interested in that depth, please look at that, and that will give you much more detail on how these things operate and why they operate the way they do. But basically, your typical house air conditioner, if it's sized properly, does a lot of moisture management, and it does it very, very efficiently. A smart heat pump ventilator, such as our Serve ventilator, and as far as we know, it is the only smart heat pump based ventilator anywhere. And so in order to get the smart side of things, you need the air quality controls on top of the other operational modes that the Serve has to efficiently and effectively manage your house energy and air quality on top of moisture. But it contributes to dehumidification. The new era of heat pump water heaters, which are starting to take off in every home, whether it's a replacement water heater, whether you have gas now, it should transition to heat pump water heaters. This is a disruptive technology. It's a great technology. It not only is the most efficient way to heat your water, it interacts both winter and summer in all homes throughout North America and basically throughout all climates. You can read more about that in our various newsletters and reports as well, why this works so well even in northern climates where many people believe it's a detriment. It absolutely is not. But in the summer, it is an important contributor to moisture management. And then finally, when conditions dictate, and basically those conditions are when the sensible heat ratio, the ratio of cooling needed to change the temperature in the house, basically the sensible cooling, to the total cooling, which is the sensible plus the latent, the moisture. When the latent cooling becomes more than half of the cooling load, this is when dehumidifiers especially are needed, and Miami, as we'll see, is a good example of that. So we'll look at that further in this example. For sure, there's other ways to dehumidify, but these are not on the market or not readily usable by residents. And as someone who has 40 years of research background into air conditioning, dehumidification research, I've worked in many of these. I'm sure you haven't heard of electro-osmotic desiccants, and that's because we invented that process at the University of Illinois. But there's many, many phenomena for moving moisture around. It's just that they're not simple enough or cost-effective enough or developed enough to be used in our homes at this point. As far as an air conditioner, a typical 1-ton, say mini-split air conditioner, which is growing rapidly in homes, new homes, existing homes. These are fantastic machines, and to get more background on that, you can read our report, Minisplit Mania, which gives you much more background on how these operate. But mini splits are also good dehumidifiers, and when they're put into dry mode, they can have a sensible heat ratio down to about 0.5. And they'll pull out about 40 to 80 liters per day, depending on the humidity condition and the climatic conditions that it's working with. And so this is your first line of defense in a home. Typical air conditioner is just a bigger unit than a mini split. And the main thing about it is, as it removes energy from water vapor as well as cools your air down, that heat's deposited outside as well as the water being removed from your home. This is a performance plot for one popular 1-ton mini split, but a 3-ton central air conditioner looks very similar to this. It would have a different scaling, of course. And the area where most homes feel comfortable, as we discussed, this humidity ratio on the bottom scale is somewhere around, say, 0.009 to 0.011, about 1% water mass in the air mass. The performance data for this mini split somewhat bouncing around here, and that's because with today's inverter drives and variable speed fans that it has algorithms adjusting it. But roughly what you see is that it increases in humidity handling capability as humidity ratio, as the humidity goes up. And then it drops off, or basically shifts more of its cooling capacity into sensible as the humidity lowers, which is a trend that we like. As far as the sensible heat ratio, in typical operation condition, most air conditioners operate with about a 70% sensible heat ratio, meaning that 30% of their capacity is going into dehumidification. But for systems such as today's high performance mini splits, they can be operated in a dry mode with a compressor speed relative to an airflow over the cooling coils that enhances their dehumidification. And that has them operate down to about sensible heat ratios of 0.5. Now, a smart conditioning ventilator such as our SERV, when it's exhausting indoor air and then bringing in outside air, if it's humid and warm outside, we can pull out about 10 liters of moisture per day out of that outside air. And getting that moisture out of the air when it's most humid, instead of bringing that air in, mixing it with the inside, and then letting the mini split or some other dehumidification unit handle it, there's an advantage to that. The more concentrated, the higher the humidity of that air that you run through a dehumidification system, the higher performance you'll get on that side. And so, but basically, within this discussion, we're up to about 10 liters per day capability in our ventilation system. And when we look at hybrid or heat pump water heaters, these scale with the number of people in a home and their shower activity. And basically, from our field data, we find that a typical heat pump water heater pulls out about a half a liter per day per person. If there's no one in the house, no hot water is needed. It pulls out very little moisture. When a lot of people are in the home, it increases. So it scales nicely with occupancy, and we'll see that in the field data. Finally, I'll mention on a dehumidifier, and you can get as many liters per day capacity, whether it's a basement dehum like you'd buy in a big box store for a couple $100, or an inline ducted high quality dehumidifier, as you'll find, that these can operate below a sensible heat ratio of 0.5. That is, they can operate with a load that's dominated by latent. And what's interesting about this is that because the unit is contained within the house, the heat that's pulled out of the water to condense the water vapor and the compressor power that's put in for driving it, that's released as heat inside the house, which increases the cooling, the sensible cooling load of your air conditioner. And so it's actually a nice match with an air conditioner when you have excessive dehumidification conditions that need to be managed. It bumps up the sensible heat ratio for your standard air conditioner while getting rid of moisture that air conditioner cannot remove. Now, as far as dehumidification efficiency, dehumidifiers are, for Energy Star, are rated on an energy factor, kind of like a heat pump seasonal performance factor or a SEER. In this case, it's the kilograms of water per kilowatt hour that can be removed per day from a home. That rating occurs at 80 degrees Fahrenheit. And so for a house at 80 degrees Fahrenheit, that operating within the house, Energy Star rating requires an energy factor of 2 or greater. And the two open circles above 80 degrees Fahrenheit with a relative humidity of 60%, which is a very, very high. This would be a very uncomfortable home to be inside of for that dehumidification condition. But these two dehumidifiers, the two open circles, operate quite high, about 2.5 to 3 kilograms per kilowatt hour of operation. And that's in comparison to where we used to be, which was around 1 to 1.5, or where non-Energy Star, like cheap basement dehumidifiers, would be operating at. Now, when you bring that more to typical indoor conditions, say in the 68 to 75% range and about 60% relative humidity, notice that those open circles at that performance level drop. So the Energy Star rating is actually a very high rating of performance for that dehumidifier. When you operate that at indoor conditions that we would typically maintain in a home, you're dropping by a significant amount, 15, 20%. Furthermore, as I mentioned, that the dehumidifier is dumping heat into a home, and the air conditioner has to make up for that. If we assume at 80 degrees, the Energy Star rating, that we had an air conditioner with a coefficient of performance of about 3.8, and this would be an Energy Star air conditioner, something with a SEER value greater than 14 or so, that energy factor now, an adjusted energy factor for the open circle dehumidifiers, that has dropped down to about 1.5. Now, the lines that are plotted on this are the energy factor of, say, a Minisplit air conditioner that I just showed. And you can see that it actually, as a dehumidifier, compares very well to the adjusted dehumidifier that then has to have its heat load adjusted out. And this energy factor for the Minisplit does not account for its sensible cooling. This is only looking at the amount of water coming out of it relative to the power to drive it. And so in effect, this is not directly an apples to apples, but favors the dehumidifier unit. And if we added in that additional sensible cooling benefit, the Minisplit or standard air conditioner would look even better. We go to comfort conditions and we see the same trend. The air conditioner would be operating at about 3.3 rather than 3.8 coefficient of performance, but the trend is the same. The air conditioner, the sample Minisplit in this case, is operating with a higher energy factor than a dehumidifier. Now, this isn't saying don't use a dehumidifier, it's just saying that in terms of preference, get moisture out with your air conditioner as much as possible. And then as you start exceeding that, stage it so that your dehumidifier then kicks in for additional high levels of moisture. So now let's look at some real data. Here's Equinox house. It's a 0+ house, has been every day of its life since it was built almost 10 years ago. 2 electric cars are fed off of the 8.5 kilowatt array in the backyard. This is also the first home in Illinois in a municipality allowed to collect and harvest rainwater that can be used indoors. And so it has several unique features. And again, a lot of these reports and writings are included on our website. So this has a 1-ton ducted Minisplit heat pump, a smart heat pump ventilation system, and a heat pump water heater. And here's some data. And in the report that we posted in October on these dehumidification systems, there's 4 summers of data located in that report. So you can see between a humid summer and a dry summer, this is our typical summer, but fairly humid. And over the course of the summer, we pull out about 700 liters of water going from May up through September. And you can see how the moisture is divvied out. The heat pump, the Minisplit heat pump does the heavy lifting. About 60% of the water is pulled out by that. The smart ventilator, the Serve Smart Ventilator, which the original Serve installed 10 years ago, is the unit that operates today. That pulls out about 1/3 of the water. And then the heat pump water heater And you can see the heat pump water heater is pretty linear. It doesn't have this kind of stair-step case, which is kind of dry periods and wet periods that reflect the outdoor humidity conditions of the Minisplit and the serve ventilator. Instead, it goes more with occupancy. Taking 2 showers a day every day takes about that much water out of the house. Now this, if you look at the middle of the summer and say over the course of July, going from about 200 liters up to about 500 liters over about a 1 month period, that's about 7 liters per day. And from our example problem for a tight home in Urbana, a 2,000 square foot home with 2 occupants, we came up with about 6 to 7 liters per day. And so we're in very good agreement, and this is without trying to fudge anything. This is real data, condensate data collected every day from each of these systems for 4 to 5 years. And the modeling is taking our average weather and finding out that, hey, these calculations actually work. When we look at the daily details, here's that same summer. Hot, humid weather comes in. Thank you, New Orleans, for that. We get up to 20, 25 liters per day. Maybe we had a party. We've got a bunch of birthdays in July when people come over. And then other days where we may not be home or the weather is drier, we're getting cool weather at night. And so the serve automatically goes into a free cooling or free fresh air mode that we can pull moisture out that way when outdoor is nice. But we see that we need to be prepared for quite a bit of moisture handling, even in a very tight home. And this bucket is one of the buckets that gets used to collect condensate. This is actually for an outdoor experiment. All the data that was in the previous slide was from indoor collection points in Equinox house. So let's look at Miami. In our report, we look at monthly characteristics for Miami, Phoenix, and Urbana because they're nice displays of what goes on in a northern climate like Urbana to a southwestern dry climate like Phoenix to a southeastern climate like Miami. And we'll look at contractors loose, tight, and smart again. We'll look at some characteristics of these homes on overall house basis. And finally, what the impact on energy is. Well, when we look at contractors loose, tight, and smart for every month of the year, we see that Miami, hands down, it's a wet environment. We work a lot in Florida with a number of air conditioning and dehumidification systems for other applications in addition to this. There's no doubt about it. Key West through most of Florida, you've got a lot of moisture to manage. But tightening up the house, you see a significant improvement, and then smart ventilating a house. Ventilating when you really need it and not ventilating when you don't, you see another significant drop. Not so much in the winter months, as the humidity outside isn't so different from inside and is fairly pleasant, but definitely in the summer months, very heavy. We look at what this means as far as heating and cooling capacities. And this is thermal kilowatts, not electric. So it's not the plug end of the air conditioner. And the cooling capacity is the sensible cooling, the cooling needed for changing temperature. Miami needs no heating. So as you look at the report and see Urbana, you'll see quite a bit different. But what you see for contractor loose is that the sensible heat ratio is very, very low, well below 0.5. You've got to dehumidify in this house. As we go to contractor tight, the sensible heat ratio comes up. The latent capacity, though, is still significantly greater than the sensible cooling capacity needed. And as you smart ventilate, on average, you see that the smart ventilator will increase the sensible heat ratio up to about 1/2, where the typical air conditioning system coupled with smart ventilation, heat pump operation, and heat pump water heater operation can maybe manage on average the moisture. But again, looking at that capacity chart, that daily capacity chart, most likely you would want to have a dehumidifier in addition to the standard cooling heat pump. And but stage it so that is not always running, because your higher efficiency with today's modern variable speed drive heat pumps will give you a higher energy factor than a dehumidifier. Looking at the energy, the overall, now this is plug energy. This is kilowatt hours of electricity. We see that Contractor Loose's home, you're going to be using almost twice as much energy. Now, part of the infiltration load is the sensible cooling load, and that's included in this, as well as hot water and lights and cooking and the kitchen sink and everything, the occupant related loads, as well as the building shell and window loads. Before this typical 2,000 square foot home located in Miami, you can see almost a 50% reduction in its energy needs. And this, is going to save a lot of money as well. Maybe a $1,500 to $2,000 per year annual utility load or electricity, down to about maybe $800 to $1,000 utility bill. Brief mention on household humidification, but again, with very well sealed and well insulated homes in northern climates, and with smart ventilation, your humidity level should certainly stay above 30%, if not 40%, as an Equinox house. If you do find you need humidification, we would lean you towards steam or vapor injection, where you're heating the water and boiling it, and it's going in as a vapor, as opposed to droplet or cold water injection, where droplets are sprayed and then it's energy from the air that then vaporizes the water. Now, the steam vapor injection, all of the energy needed to vaporize water, and it takes about 2/3 of a kilowatt hour to take liquid water and turn it into vapor. That's an inefficient process. To be much better to vaporize that water with a heat pump and get maybe a 3-to-1 return on your electric energy. Cold water injection or droplet evaporation, it is in effect, if you are heating your home with a heat pump, getting that 3-to-1 energy benefit in vaporizing water, but it comes with some problems. Both of these need to be maintained for scaling and scum and other stuff forming in the reservoirs. But the cold water especially can be a breeding ground for things like molds, mildews, bacteria, endotoxins, and you need to keep on top of it. And so sanitizing, keeping that sanitized is extremely important. Several studies have shown that that these cold evaporators are very large generators of endotoxins, and our report on endotoxins will familiarize you more with their detrimental effects. So best to avoid humidification. Plants are great. As I mentioned, we've got 50 plants in our house, about 6 liters of water per day to 7 liters in the wintertime, or per week, are vaporized. And something about the plant root dirt matrix sanitizes that water, so as it releases it as a vapor, your house is providing the heat to the plant to help it vaporize that water. So you are getting that heat pump efficiency in vaporizing water, and you're getting nice sanitized water, as well as the air quality benefits of plants. So we highly recommend that. So in summary, seal homes tight everywhere, all climates, ventilate smart, and if you do that, moisture management will be much easier. You'll be able to manage moisture in humid regions. You'll be able to manage moisture in cold, dry climates. And humid moisture is important. You got a party, you're cooking spaghetti, people are dancing and active. It can be the driving force, or you're cooling anything with a lot of people in it. We put out a lot of moisture, but in the typical house with the typical occupant density in a house, while we want to account for it, it's not the big dog relative to climate typically. And finally, as we saw, the energy related to moisture, and while we just showed Miami, as you read about Phoenix and Urbana and anywhere else, the impacts of sealing up on energy and related to moisture are very, very important. So thank you very much for taking time out of your busy days to participate in this. I hope that this gives you some ideas and some background for being able to design homes that are managing moisture. It's just extremely important for the health of the home's occupants, and it's not that difficult to do. Thank you very much. Bye-bye.